I have to have a list because of the many things that Dr. Jessie Christiansen has been doing and is continuing to do. So, but we're really thrilled to have her here tonight. She's a very busy lady. I talked to her as she was getting on a plane last week, and she's getting on a plane tomorrow. So we're lucky to have her, and I think you'll really, really enjoy what she has to talk to us about. Of course, she'll be telling us all about these exoplanets and maybe finding another planet like ours and what that might mean to us. But first, let me tell you just a little bit about Dr. Christiansen. She grew up in a very small town in Australia, and after testing a few interests, like becoming a fighter pilot, I hear, she gradually found her way to astronomy and received her PhD at the University of New South Wales. Bugs, sorry. After a bit of research in Antarctica, Dr. Christiansen came to the United States for postdoc work at Harvard and Smithsonian Center for Astrophysics. And then now today she's a research scientist at Caltech and works with the NASA Exoplanet Science Institute at Caltech /IPAC. And you can ask her what IPAC means. She is also the lead scientist for the NASA Exoplanet Archive and has worked on the Kepler, K2, and Tess missions. Because of her strong belief in the value of public outreach, she is also a TED Fellow, does all those TED Talks, and an active mentor for underrepresented minorities in STEAM, science, technology, engineering, art, and math, while striving to be a role model for younger girls. And if that's not enough, she also has a family with 9-year-old twins. So please join me in welcoming Dr. Jessie Christiansen.
Thank you, Katie. Hi, everyone. Thank you so much for coming out tonight. Actually, a little upgrade on the list. I got promoted a couple of weeks ago, and I didn't tell Katie, I'm now the chief scientist of the NASA Exoplanet Science Institute. Which is a really fancy title, but the previous person who had the job hasn't given up any of their tasks yet. So for now, it's just a cool title. So it's my real pleasure to be here tonight to talk about, honestly, one of the oldest questions of humanity, a question that has driven religion and philosophy and science for thousands, if not tens of thousands of years, which is, are we alone? Now tonight I'm going to focus it down a little bit and I'm going to talk about specifically one of the questions we're trying to answer on the way to the question, are we alone, which is the search for Earth 2.0. Now in the Q&A we can talk about why we're focusing on the search for Earth 2.0. Take it as given, that's what we're going to talk about for most of this. There's other places to look for life, but we're talking about Earth 2.0 tonight. Okay. So here is a schematic of the solar system, not to scale. We have one star, which is the sun in the center of our solar system, still up right now. You won't be able to look through those telescopes for a little while yet. We have 8 planets. Boo, hiss. I know, I'm sorry, I wasn't there, I didn't vote. We have 8 planets. We have a bucket full of dwarf planets, and if you ever feel bad for Pluto, Pluto didn't just get to be the worst planet, it got to be the best dwarf planet. That's pretty cool for Pluto. It got to start a whole new type of object called dwarf planets. We also have minor planets. This is everything else in our solar system that we've managed to catalog. There's over 1 million things out there that we've found and tagged. Space is really big and really empty and has a lot of stuff in it. But what are exoplanets? Katie mentioned that what we're going to talk about tonight are exoplanets. Exoplanets are planets around other stars. So let's talk about the history of that. Now, as I said, we've been thinking about this for a long time. You can go back to the Greek philosophers more than 2,500 years ago. They were already thinking about whether or not Earth was singular or plural. And it's really interesting because Plato and Aristotle actually argued that, there was only one Earth, there weren't going to be any other Earths. And the way the Greek philosophers talked about all of these things was hypothetically, right? They didn't have a way of testing it yet. These were really cool thought experiments. And it's kind of the way we think about multiverses today, right? Like, it's a really cool idea. Let's think about it a lot, but we don't have a way of testing it at the moment. But this is the way they were talking about Earth. Is Earth singular or plural? Okay, let's leap forward to the Italian Renaissance. This was a fantastic time in Western Europe for art and literature and science and math. Wasn't a great time to say anything stupid about the Roman Catholic Church, which this guy did. His name was Giordano Bruno. He was an Italian mathematician and philosopher. And so thousands of years later, we know that the other stars in the sky are stars, and our sun is a star. And so Giordano Bruno is like, okay, there's countless stars. I think there are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. I will leave it as an exercise to the interested reader. What 7 is he talking about? Okay, so he said this, which was actually quite in conflict with Roman Catholic doctrine at the time to claim the plurality of worlds. And it was one of the reasons that Giordano Bruno, 8 years later, was burned at the stake. I'm very lucky here in 2024 that we don't do that to people who are looking for planets anymore, which is good. Okay, so we have this idea. They've already gotten to the stage where, like, there's other stars, they might have planets around them. But again, the technology's not there yet. There's no way of finding them. In 1952, astronomer Otto Struve, it's this incredible paper. I know probably you don't go and sit and read a lot of journal papers, but it's amazing. It's from 1952. It's only 2.5 pages long. And he's like, what if we could measure the velocity of the stars that the planets were orbiting around and measure a change in the velocity because the star is being dragged around by the planet? Now, they'd already done this for binary star systems, 2 stars going around each other. You could measure the velocities of the stars and see that they were going back and forth very quickly. And you could see that they were orbiting each other. And he was like, okay, what if we took out one of those stars and put in a planet? The wobble would be much smaller, but if technology got good enough, we could see it. So he's coming up with these methods. He's like, we think they're there, how are we going to see them? So he comes up, he describes in this one paper, this radial velocity method is what we call it now. It also, right at the end, has a paragraph, just like, also if those planets went in front of their stars, they'd eclipse the stars, and we might be able to see a change in the brightness of light. One paragraph. We're going to get to that method, the transit method, later. Anyway, in his math, when he's working this out, he's like, it would be obvious, if you could see this velocity, if the planet that you were looking at was a giant planet, like Jupiter, like one of the giantest planets in our solar system, and you put it right next to the star. So it was going around very quickly, and then you would see a velocity change. So he comes up with this idea. And everyone's like, Otto, that's crazy. You can't have giant planets right next to the star. We know how planets form. You get small rocky planets close to the star, and big giant planets far away from the star. You can't have a giant planet right next to the star. So between 1952 and the next 4 decades, this paper has 7 citations, because everybody just thought this idea was crazy, that you could have gas giants right next to the star. In 1995, the first planet was found orbiting a star like the sun using Otto's method, and it was a giant planet orbiting its star in a few days that we now call hot Jupiters. That planet won the Nobel Prize in 2019, the discovery of that planet. So these were real. Hot Jupiters, we call them, because astronomers shouldn't be allowed to name things. They're Jupiter-sized planets right next to the star, so they're really hot. That's it. That's all the thought that went into it. And they were this first type of planet found around another star like the sun. And it kind of blew everyone away. Since then, that paper that I mentioned has over 100 citations. You know, this feeling in science when you're vindicated. I was right. He was right. It's a good feeling as a scientist. Okay, so that's 1995. That's only 30 years ago that we found the first planets around sun-like stars. What's happened since then? Okay, this is a really cool sonification of data that was commissioned by NASA. What you're going to see is every time we find a planet, as time passes, it's going to appear on the sky. The pitch of the note that you hear is how fast it's going around its star. And the color of the point is how it was detected. So here, let's play it. So it starts in 1991. We do have some pulsar planets in 1992. Okay, 95 is the first sun-like star with a planet. 96, things start to heat up. 99, I graduate high school and wonder what I'm going to do with my life. 2004, I start my PhD and start searching for planets. 2009 is when the Kepler mission launches that we're going to talk more about. Kepler stared at one patch of sky. You'll begin to see it pop out real soon. Can you see where Kepler pointed? All right. At some point, Kepler isn't able to look at its original field anymore and starts to do an ecliptic plane survey. So you're going to start to see this curvy sine wave through the picture. That's K2. So in 2022, when this was made, we had just hit 5,000 planets. So we went from none to 5,000 in 3 decades. And it's been exponential growth. And since COVID, everyone has a much better idea of what an exponential is. So that's really helped my science communication. You guys all know things get faster than they get faster. Okay, I'm going to show one plot in this talk. It's this plot. We're going to see it a few times. Stick with me, and you'll be able to follow it. I promise. On the x-axis, the horizontal axis, this axis here, I'm plotting how long it takes that planet to go around its star. So how long does it take Earth to go around our sun? 365 days. Okay, so 365 days is out here. There's 100 days, there's 1,000 days. On the y-axis, I'm showing the size of the planet relative to Earth. So Earth is 1. And in fact, this little pink square here, that's the Earth. And these pink squares are our solar system planets, Mercury, Venus, Earth, and Mars. That's what we knew before we started finding exoplanets. So you can see, this is what we knew before the launch of Kepler. Up in the top left, those are giant planets really close to the star, right? They're orbiting in just a few days. That's the hot Jupiters. That's this first new type of planet that we found when we started finding planets. Incredible class of planets that opened up, hot Jupiters, and we're still studying them today because they're so interesting. But what you can see, what we hadn't found before Kepler was anything that looked like any of the planets of our solar system. Our solar system is way down here. Turns out the rocky planets in our solar system are really small, especially compared to things like Jupiter. All right, this is what it looks like closer to today, and this is Kepler. Kepler has done almost all of this heavy lifting. I'm going to talk more about Kepler, but you can see we've really filled in the space between the hot giant planets and the cool small planets. So these are intermediate warm planets, and basically we call them sub-Earths and sub-Neptunes and super-Earths, because we shouldn't be allowed to name things, because they're between the size of Earth and Neptune. So this is an incredible diversity of planets that don't look anything like our planets, right? Before 1995, if you were a planet formation theorist and your planet formation theory didn't basically recreate the solar system, you put it in the bin because it was wrong. What we've discovered is that nature is much more imaginative than we are, which is true through many natural sciences, and there's incredible diversity of planets that we found. Okay, let's talk more about the search for Earth 2.0. So we'd found hot Jupiters, right? But thinking about this big question, are we alone? Where's the only place we found life so far on Earth? Why aren't we searching for Earth 2.0? Along comes the Kepler mission. So this was a 1-meter optical telescope that was launched in 2009. These are the solar power that you can see, the solar panels. That's the opening at the top where the light comes in. There's the Earth in the background. It was in a heliocentric orbit, so it followed the Earth around the sun, basically like a puppy. As the Earth went around, Kepler was like, yeah, I'm coming. And then you can see the high-gain antenna on the bottom right. That's how we sent the data back to Earth. That's Kepler. So Kepler looked at that one patch of sky that you all saw in that video, and we just stared at 200,000 stars in this patch of 10 by 10 degree sky for 4 years straight. Just did nothing else except stare at that patch of sky. And actually it's very visible from the summer in North America. If you can find Cygnus, and I know we have some amateur astronomers in the audience, Cygnus is the Swan, it's one of the big bright constellations that's overhead. It's between Cygnus and Vega. Vega is one of the brightest stars in the sky. So this patch of sky, we know we have found thousands of planets in that little patch of sky, which is pretty incredible. But Kepler wasn't actually launched to find thousands of warm Neptunes. Kepler had one goal. How common are planets like the Earth? Rocky planets in the habitable zones, the right distance from the star to be not too hot and not too cold, of sun-like stars. That's the 3 criteria. Rocky planets, habitable zone, sun-like stars. Kepler's goal was to answer this question. Kepler used the transit method. Here we go. So let's talk about what the transit method is. You've all now heard about the radial velocity method from Otto Struve. In his paragraph at the end of the paper, he just pithily throws off this idea: what if they eclipse their star? So this is an animation of a system called TRAPPIST-1. TRAPPIST-1 is the name of that very small, cool red star in the middle. It's actually much smaller and cooler than our sun, and in fact is just about as small as you can be and respectably still call yourself a star. If it was much smaller, it would be a brown dwarf. But it just squeaks in, it makes it. And it has 7 rocky planets around it. And I will start again. So these are the 7 rocky planets. 3 of them are in the habitable zone of this star, the middle 3 of those 7. There's 2 that are too close, 3 in the habitable zone, and then 2 that are too far, they're too cold. So most of the time you have no way of seeing these very, very small planets. They don't weigh much, so they don't cause a lot of wobble on the star. But sometimes they're lined up just right. You take that planetary system and you line it up. From our point of view, all of those planets pass between us and that star and block some of the light. So this is data from the Spitzer telescope. So that all of those white points, that's just measurements of the brightness of the star over and over again. And what you can see as the animation shows, every time a planet goes in front, the light drops. Some of the light gets blocked. And if folks here went to the solar eclipse just a few weeks ago, back in April, that's what this is. It's something going in front of the star and blocking the light. Now, it's a very simple measurement. Like, measuring the brightness of stars is one of the oldest astronomical measurements we have. But you can learn so much. So the distance in time between 2 successive transits, we call them transits because the planet's transiting in front of the star. The distance in time between 2 successive transits is its orbital period, its year, how long it takes the planet to around the star. And then the depth of the dip tells you how big the planet is. Big planets block more light and small planets block less light. So the fact that you can see all these dips have different depths tells you these are all slightly differently sized planets. So that's the transit method. And that's what Kepler used. So, one goal, 200,000 stars, 4 years. Did we do it? Yeah. We didn't find any planets like the Earth. That little pink part of the is still empty. We don't have any planets that are like the Earth. We got close, we got bigger planets and we got hotter planets, but we didn't find any Earth-sized planets in the habitable zones of sun-like stars, which is a bummer when it's your #1 goal. And we can talk later about what led to that, but basically we didn't get there. And I'll say that this bottom envelope here, where the planets start to drop off, that's the detection sensitivity of the telescope. That's just where we're not sensitive anymore. The planets get too far away and too small, and we just can't see them in the noise. So that drop off there, we don't think it's real. We don't think there are no other Earth-like planets. Just turns out Kepler couldn't quite get there. But we have a lot of other data, and that's all really cool. But we don't know really the answer yet. But if you give scientists some data, they will work with it. And we do something really dangerous called extrapolation. You should never do it, but we do it because we have data. So what we do is we extrapolate from the shorter period planets, the hotter planets, and the larger planets, and we say, if that continued, what would the rate be? And if we do that, which is dangerous, we think that something like 10 to 50% of stars like the Sun have a planet like Earth. That's pretty incredible. There's a lot of error bars on that, and even 10 to 50% is a factor of 5. But we don't think, given how common these planets are that are smaller and hotter, larger and hotter, we don't think that Earth-like planets are rare. We think that they're very common. We just didn't find any with Kepler. Okay, so what did we find? This is Kepler 452b. I'm apologizing right now. Exoplanet names are garbage. We didn't get it right, and now we're stuck with this terrible way of naming exoplanets. They're either named after the star, if the star already has a name, and then we put B, little b at the end for the first planet, or they're named after the survey that found them if the star doesn't already have a name. Kepler 452b was the 452nd planetary system confirmed from Kepler. It's terrible. They all have just phone number names. Anyway, Kepler 452b. This is as close as we got. It's about 1.5 times the size of Earth in terms of radius. And that's a worrying thing, because once you start to get that big, you start to become something more like a mini Uranus or a mini Neptune. We think that at some point you transition from being predominantly rocky with a thin atmosphere like Earth to something with a much thicker, much bigger, much deeper atmosphere. So at 1.5, we're not sure. Could be rocky, but maybe it's not. It is in the habitable zone, so that's good. It's the right temperature such that if it was like Earth, you could have liquid water on the surface. And that's one of the criteria that we like to check off when we're looking for life, liquid water. And it's orbiting a star like the Sun. That's great. The problem with Kepler 452b is that it might not be there. Unfortunately, there's a lot of noise in the data, and the signal that Kepler 452b presents looks just like the noise, so it's kind of like, so doing a whole bunch of really rigorous statistical tests, we give it about a 50-50 chance of being real. So you wouldn't like get in a Tesla and launch yourself there right now. We don't know if it's there. That's as close as we got with Kepler. But we did find other things. So I mentioned that TRAPPIST-1 is a small, cool red star. We call them M-dwarfs. And actually most of the stars in the galaxy, 75% of the 100 billion stars in our galaxy are M-dwarfs. So they're much smaller and much cooler than our sun. We did find a lot of rocky planets in the habitable zones of M-dwarfs. This is an example. This one wasn't found by Kepler, but it's a lovely graphic, so I'm using it anyway. This is the rocky planet in the habitable zone of Proxima Centauri. So when you think about our neighbors, how close planets could be, planets can't get closer to us than Proxima Centauri. It's the closest star to our solar system. As you move out, it's the first one you hit. It's actually in a triple star system with Alpha Centauri A and B, which is this little bright pair back here. So those two are sun-like stars, and then Proxima Centauri is an M-dwarf, a smaller, cooler star. And it has a planet in the habitable zone. The very closest star to us has a rocky planet in the habitable zone. That's bananas, right? If you were going to go borrow a cup of sugar, this is where you're going. Now, the problem with this is the star is very different from our sun. We don't know exactly what caused life on Earth to start, right? There's so many variables. But we do know that M-dwarfs have very different radiation profiles from our sun. And in particular, they put out a lot of their energy as high energy radiation, so X-rays and UV. So I'm from Australia. We had a hole in the ozone layer for a long time. UV is bad for life, right? We use UV light to sterilize equipment in labs. So if you're a rocky planet next to a star putting out a lot of UV, maybe it's not great. And X-rays are the reason they make you wear a lead apron at the dentist, right? X-rays are bad. So we don't know yet whether these rocky planets around M-dwarfs receive too much high energy radiation for us to think about life. One thing I'll say is that the habitable zone of these very small, cool stars is much closer than our habitable zone. So Proxima Centauri, I think it's like 2 weeks it takes to go around. So they're pretty close to these stars, but the stars are so cool, they don't heat up too much. So the jury's kind of out on this one. We have found rocky planets in the habitable zones of M-dwarfs, but we don't know if they're habitable yet. So far we have found 14, actually got to update this slide last night because a week ago 2 more were announced. This said 12. So there's 14 of these rocky planets in the habitable zones of M-dwarfs. That's pretty exciting. But we don't know if they're Earth-like, right? Coming back to the topic at hand, the search for Earth 2.0, we don't know what these planets look like. All we know is their size and their temperature. They might not have atmospheres, they might not have the capability for liquid water, they might not have life. So how are we going to answer this question? How do we know if these 14 are Earth 2.0? With the James Webb Space Telescope. And we'll see if I can get the title up. There we go. Okay. So the James Webb Space Telescope is NASA's most recent flagship mission that was launched a couple of years ago. It's a 6.5-meter infrared telescope. It unfolded in space. Basically, the entire astronomy community just sat there for like 6 weeks going, oh my God, don't break, oh my God, don't break. Because there were literally thousands of moving parts that all had to move. We couldn't fix it if it broke. It had to work perfectly. And it did. NASA's great. So one of the really exciting things that James Webb Space Telescope, JWST as we call them, will do is to be able to ask the question, do these planets have atmospheres? Now, whether or not it has an atmosphere is actually quite important for life as we know it. The only way to keep liquid water on a surface is with an atmosphere. If you put a puddle of water on the moon, it's going to evaporate out into space because there's no pressure holding it down as liquid water. So we think an atmosphere is important. So even if it's the right temperature for liquid water, if there's no atmosphere because it's so close to the star, we don't know. So we're very excited that JWST is looking at some of these planets in detail to see if they have atmospheres. So far, the two closest ones to TRAPPIST-1, B and C, don't have atmospheres. That's probably okay because they're so close. They orbit in like 1 and 2 days, very, very close. But it's not great. So we're still waiting for the results on those 3 habitable zone planets, which are, the data have been taken and are being analyzed right now. Okay. All right. So, no Earth 2.0s yet. But I didn't want this talk to be a complete bummer. So I wanted to talk about some of the cool stuff we have found. So I mentioned there's these thousands of planets that are in between the hot Jupiters and the inner solar system planets. So we have the hot Jupiters. This is an incredibly exciting new class of planets that was found. Turns out they're really easy to find, but actually pretty rare. It's kind of funny because like the first few dozen we found were these hot Jupiters. And turns out they're actually intrinsically rare. They don't happen that often. They're just super easy to find. So this is a hot Jupiter. So this is how close to the star they are, right? Like they're really close. And in this case, what you can see, the star is about to burp, or already did, and it's actually blowing off the upper atmosphere of this planet. These hot Jupiters, they're heated to thousands of degrees, and some of them are actually, sloughing off their upper atmospheres. See if I can get it to play again. So this is HD 189733b. I'm sorry. And it's one of the best studied hot Jupiters that we have. One of the things we know about it, we've been able to measure the wind speed in the atmosphere and the temperature of the atmosphere, and that the atmosphere has silicates in it. We know that the temperature is thousands of degrees. So what happens when you heat up silica to thousands of degrees? You get glass. It is raining liquid glass sideways on this planet. It's real nasty. Hot Jupiters is a really benign name for somewhere that is raining liquid glass sideways because of the temperature. Okay, down here in this bottom left corner, these are the Earth-sized planets that are orbiting their stars in less than a day, just hours. So they're almost on the surface of the star, they're so close. And what happens when you heat rock up to thousands of degrees? You get lava, so we have lava worlds. This was one of the first ones that was found by Kepler, Kepler 10. We are going to, if anybody gets motion sick, now's a good time to just like turn to your partner, look at the floor, count the beams. We're going to do a flyover of this lava world. So these planets are so close to their star that they're tidally locked. The way that the moon is tidally locked to us, which means we're always seeing the same face of the moon. It's rotating at the same speed as we are. So these planets are tidally locked. So one side of the planet is always facing that star, which is right there. So we think one side of the planet is just molten lava, right? Just a deep ocean of molten lava, and that the other side, which never sees the star, is solid rock. All of these particles are silica being blasted off the surface of this planet by the star because it's so close. Now we're going to do a fly-through. This is all imagining. None of this is, we don't know anything. This isn't real. This is not a real tourist video for Kepler 10. We know it's a rocky planet that's heated up to thousands of degrees. Everything else is artistic license. So we're flying through, over the surface. We're going to swing around at some point. About now is the time to look away if you get sick. There you go. I don't know why they put the roller coaster in there, I guess just for fun. Anyway, so these are also just completely different from anything we have in our solar system, right? So they're super interesting to study in more detail. We have a bunch of rocky planets that are warmer than the Earth that we're studying. They're still too small to study in a lot of detail. But what we did find, so we have Uranus and Neptune's, is all of these planets in between the size of Uranus and Neptune and Earth. So that's kind of interesting, because in our solar system, there's nothing in between the size of Uranus and Neptune and Earth. So here are Jupiter, Saturn, and Uranus and Neptune to scale with each other, right? Here's Earth. That's the next planet down. So we have a big gap in size between Earth and Neptune. That's Venus, Mars, Mercury. The cool part is the most common kind of planet that we found, the planet that we have found thousands of, is in between Earth and Neptune. That's bananas, right? We have 8 planets and we don't have the most common kind of planet in the solar system. If you guys ever get Konstantin Batygin to come up here, he will talk about planet 9 and why it might be the missing super Earth in our solar system. But the most common kind of planet we don't have. And that means we don't know much about them. We don't know whether they're big rocks or small ice giants. We don't know whether there's something we don't have. So we don't have hot Jupiters, we don't have lava worlds. Another type of planet that has been hypothesized that might fit this criteria is a water world. So these would be planets where the entire surface is covered in a deep water ocean that takes something like 50% of the radius of the planet is just a deep water ocean. So we have found planets that fit this size and density. The first one, GJ1214b, was nicknamed Kevin, after Kevin Costner from Waterworld. Some of the planets do have nicknames. So we don't know what they are yet, and it's really interesting to think more about what they might be, these mysterious intermediate-sized planets. Okay, what else have we found? People in the audience might recognize, maybe you've seen this before, this scene from Star Wars: A New Hope. This was in the 70s. We didn't know about exoplanets yet. And there's this classic scene, right, with the 2 stars. It's Tatooine, it's a binary star system. This is the sunset on Tatooine. We have found Tatooine-like planets. So this is a system with a yellow star and a red star, and 3 planets orbiting it. So we have found planets in stable orbits around binary star systems. We've found Tatooines. That's very cool. This is, so I mentioned TRAPPIST-1, right? TRAPPIST-1 has 7 rocky planets. What I didn't mention is that the furthest out of those 7 has a period of 40 days. So in our solar system, Mercury, which is the closest planet, has a period of 88 days. This is 7 planets inside the orbit of Mercury, well inside, they're all tucked right in there. And the only way we see this, and we've seen this over and over again, these really compact, dynamically packed systems, the only way that works is if the planets are all in resonance with each other. So their periods are all related to each other. Now we see that in our solar system, right? So the Galilean moons of Jupiter has those 4 big classic moons that Galileo saw through his telescope. 3 of them are in a 1 to 2 to 4 resonance. So every 4 times Io goes around, the next one goes around twice. Every twice that one goes around, the next one goes around once. So they're all related to each other. Their periods are like clockwork. And if you map it out, you can see this. And this is what we see in planetary systems over and over again. We see these compact systems like the Galilean moons with many planets. This is my favorite system, and it's an animation by the same person, Matt Russo, who made the sonification I showed earlier. This is a system called K2-138. K2 was what Kepler became after Kepler had a hardware failure and couldn't look at that original field anymore. It spent 4 additional years as a sequel mission called K2. So it's the 138th planetary system found by K2. And it has 6 planets. 5 of them are in resonance with each other. And they're all in a 3 to 2 resonance. This one goes around 3 times for every 2 times this one goes around. It goes around 3 times for every 2 times this one goes around, and so on. So it's a chain of 3 to 2 resonances. Now, if we have any musicians in the audience, one cool thing about resonances is that's what intervals are in music, right? Musical intervals are resonances between 2 notes. And the 3 to 2 resonance is the perfect 5th interval, which is the start of Twinkle Twinkle, right? Twinkle, twinkle, that's a perfect 5th. So this system is a chain of planets basically singing Twinkle Twinkle in a blender. So let's put it on. This will be your moment of Zen. So the highest pitch you hear is the innermost planet going around quickly, and the lowest pitch you hear is the farthest out planet going around slowly. reason it has a rhythm is because of the resonances. So that's a really cool system. The thing that makes it even cooler is that it was found by citizen scientists. So Kepler and its sequel mission Tess that I'm going to talk about brought down just so much data. Hundreds of thousands of stars, millions with Tess, many, 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 many data points. Now, we've written software algorithms to search those data for planets. We say, look for a periodic dip in the light curve, and the software does the best job it can. But it can't do as good as a human. We are incredibly good at pattern matching. It is evolutionary biology. You needed to be able to tell the difference between a tiger and the grass, right? Stripes, which one's a tiger, which one's grass? So our brains are just hardwired for pattern matching. So what takes years to write an algorithm and train that algorithm and refine that and iterate it and get it right, I can show you in 2 minutes how to find a transit in a light curve. So what we do with the Kepler and the Tess data is put it online. So you guys can just go look at it and find these dips. If you have hundreds of thousands of volunteers, suddenly it doesn't sound like that many stars, right? If everyone can look at every star really carefully, you're finding planets. So K2-138 was actually found by citizen scientists in K2 data. And right now, because Tess is currently operating, we have Tess data coming down to this website, planethunters.org, very regular. I think once a month, new data get put there. And you can help us find planets. The 4 citizen scientists that helped me find the first 4 planets in K2-138 got to be co-authors on the paper that was published announcing this. And one of them got to be interviewed on TV because it was so cool. So if you're interested at all in finding your own exoplanet, you can do it. planethunters.org, there's data coming down all the time. So that's a fun way you can get involved. So I've mentioned Tess a lot of times now. Kepler launched in 2009, and in 2018, it ran out of fuel. We got it down to the fumes, people. It was running on nothing by the end, but it did run out. Luckily, in 2018, the NASA Tess mission launched. Now, where Kepler was designed to ask this very specific statistical question, so it looked at that one controlled patch of sky over and over again for 4 years, that's that yellow notched out rectangle, Tess is designed to look at the entire sky. And to find all of the closest planets to us. So it still uses the transit method, so it's still waiting for alignments, hoping things are lined up. So there's Kepler at the top. K2, that ecliptic plane survey, are those marching along the equator. And this is the Tess observing strategy for the first 2 years. It's now in year 6. So it's actually done the whole sky a couple of times now. And the idea is that you look at all of the nearby stars and look for planets around them. And Tess is predicted to find something like 12,000 planets. So we're currently sitting at about 5,638 as of yesterday at 10 a.m. because, as Katie mentioned, I'm the lead scientist of the NASA Exoplanet Archive, and that's how we keep track of how many planets there are. So we're currently at 5,638. Tess is going to add thousands more, which is incredibly exciting. And the important thing about the planets that Tess will find, the planets that Kepler found, they're too far away because we looked at this little patch of sky very deep. So we can't really do too much with those planets we found. The reason we don't know if Kepler 452b is real or not is because it's too far away. The Tess planets were all much closer, so we can use things like JWST to look in detail at their atmospheres, at their orbits, at their surfaces, all sorts of cool things. So Tess is finding the targets that we will really, really spend a lot of time on. The next flagship mission that NASA is going to launch is called the Nancy Grace Roman Space Telescope. Nancy Grace Roman is colloquially known as the mother of Hubble. She's the person who got Hubble Space Telescope launched, so now she gets her own space telescope. Keeping the Star Wars theme going, I'm sure whoever made this animation was a fan. This is a 2.5 meter infrared telescope, and it's designed to ask 2 questions. Basically, it'll do more than that, but 2 main questions. One is to ask about dark energy. So we haven't talked about dark energy, but basically the universe is accelerating in its expansion and we don't know why. So we call that absence of knowledge dark energy. Roman is going to look at that. Roman is also going to look for exoplanets. So it's going to use a completely different technique from the ones I've already described called microlensing, which relies on gravity. It's basically magic. I think Einstein was the only person who ever understood microlensing. But importantly, Don't worry, this is the same plot, I just changed the axes label slightly. Importantly, it's sensitive to planets at a different distance than Kepler was. So the x-axis again, this is just distance from the star, normalized to 1, which is where Earth is. Earth is at 1 AU, 1 astronomical unit from the star. So this is 365 days. So Kepler, remember, we have all of these planets, here's Earth, and Kepler didn't quite get to Earth. Roman, using this different technique, is sensitive to planets further out than Earth. And what we're really hoping is that where these sensitivities kind of basically overlap, we might be able to finally constrain this question of how common are planets like the Earth. What Roman won't do is find individual interesting Earth-like planets for us to follow up. Roman, again, is a statistical mission looking at stars very, very far away. So we'll be able to constrain the question of how common Earth-like planets are, but we still won't have something we could call Earth 2.0 yet. We will, however, have something like 100,000 planets from Roman, which launches in a couple of years. So this is job security for me, since my job is to count them all. So we're going to find a lot more, and I'm going to have to build a bigger boat. If you look at the extrapolation, if you look at that exponential, we're on track in decades to find millions of planets, akin to the millions of stars that we already know. So planets are pretty hot right now. Okay, all right. So we think we can constrain how common Earth-like planets are. But we're kind of stuck because we still can't find a nearby Earth-like planet in the habitable zone of a sun-like star that we can study. We still can't find Earth 2.0. So we're kind of like the Greeks again, right? Like we have this idea that they exist, but we don't have the technology yet. This is a fourth technique that I haven't described yet called direct imaging, which is what it says on the box. You try to take an actual picture of the planet. So this is a system called HR8799. Very, very exquisite instrumentation was used to block out the star in the middle and create this kind of black void. The star is there, we've just blocked it out. And when you block out the light from the star, it's like, you know, tonight when you go out and look at the telescopes, if you ruin your night vision, it's going to be harder to see faint stars. But if you wait and get your night vision back, don't look at bright lights, you can see faint stars. We can see 4 giant planets orbiting this star. So there's one out here, one here, one here, and one here. These are all actually bigger than Jupiter and actually much further out than Jupiter. You can see this error bar for people who are interested on the bottom is 20 AU, and Jupiter's at 5 AU, so Jupiter would be well within this here. So this is a very different kind of system than ours, but it's a system where we were able to do this, to actually take pictures and see planets moving. This is actual light from those planets coming to us, which is pretty cool. So we're stuck, but we have a plan. NASA has a plan. This is our Exoplanet Mission timeline. So this is Hubble, which we've mentioned. This is Spitzer, which we talked about, that had the beautiful TRAPPIST-1 data that got retired just in 2020. This is Kepler and K2, which now you've heard a lot about, that ran out of fuel in 2018. This is Tess, which is operating right now to try and find nearby planets. Here's JWST, which is operating right now to characterize those planets in detail and look at their atmospheres. This is Roman. And then after that, we have our next plan. It's called Habitable Worlds Observatory. And it's what it says on the box. Every 10 years, all of the astronomers in North America get together and work out what's our priority for the next 10 years. What do we care most about? Importantly, where should NASA and NSF put their money? Right? Like what do we want them to buy for us in the next 10 years? And the idea being it's like collective bargaining, right? Like if we all come together and go to Santa and say, this is the thing on the top of our list, Santa will be like, okay, you've all agreed, I'm going to give you $10 billion. Anyway, so the 2020 Decadal Survey, it's called a Decadal Survey because it happens every decade, came out in 2021. COVID was bad, guys. And it included this sentence. Inspired by the vision of searching for signatures of life on planets outside of the solar system, and by the transformative capability such a telescope would have for a wide range of other astrophysics, this survey recommends that the first mission to enter this program of study described above, is a large, approximately 6-meter aperture, infrared optical ultraviolet, that's a lot of wavelengths, space telescope. So the #1 recommendation for space from the 2020 Decadal Survey was, please build us a big telescope to look for Earth 2.0. which has now been called Habitable Worlds Observatory. NASA has taken that advice and convened a group of scientists called the START, Science, Technology and Architecture Review Team. So there's 20 scientists all around North America who are going to design Habitable Worlds Observatory. I'm lucky enough to be one of them, which is why I get to talk to you about it. Katie mentioned I'm on a plane tomorrow to fly to Baltimore to spend Monday, Tuesday, Wednesday with those 20 scientists sitting down and really hashing out what we want this telescope to be able to do. And what we want this telescope to be able to do is to image Earth 2.0. So here's HR 8799 again. We want to do that, but for a system like our solar system. So this is a simulation of what that might look like if you were about 30 light years away from us. If you were a star about 30 light years away looking at our solar system with something like Habitable Worlds Observatory, this is what you might see. So Jupiter is a big booming signal. You can see Earth, and maybe you just get Venus. But the idea is to design it so that you can get Earth. So we have a plan. And I just want to throw one more plot. It's okay, it's one more plot. This is just to show that we have an idea of what biosignatures might look like. Biosignatures are evidence that you would find on a planet that there's life. Biosignature, the signature of life. The biosignatures on Earth have changed a lot in the last 4 billion years. If you were an alien civilization looking at Earth 4 billion years ago, you might not think that there was life like the life we have today. That atmosphere looked completely different. And it has evolved over the last 4 billion years to now look like what we see and breathe today. So this is just another really interesting thing to think about. How has Earth evolved with time, and what does that mean for what we're looking at? So, Habitable Worlds Observatory is getting planned now, won't fly for 20 years. I'll be realistic, not going to fly for 20 years. But in 20 years, we launch a space telescope that can find Earth 2.0. Count on it. So now imagine yourself 20 years from now, and we've discovered Earth 2.0. We've found a planet that's rocky, it's the right distance from a star like the sun, it's got an atmosphere. Maybe it has liquid water. It looks like Earth. What does that mean for us? So we've been asking this question for a long time, are we alone? Right? Like if we find a planet with life on it, what does it mean? What does it mean to us? We actually have some historical examples of how people have reacted to the potential for life. This was in the 1930s. There was a radio broadcast of the War of the Worlds. Some people missed the intro to the radio broadcast, that it was a story, a fictional story, and thought that Earth was actually being invaded. Now, this has the element that Earth was being invaded here, but there was panic, right? Actual panic. This was frightening. Let's jump 40 years into the future. We have the WOW signal. So this was a radio telescope in Ohio in the 70s, was listening, and one day a person's looking through the data and they see this incredible, huge, booming signal in this little patch of sky, and they write WOW beside it because it's the biggest signal they've ever seen. This one, there was excitement and optimism and funding, and people have thought a lot about this over the years. There was a GoFundMe only in the last few years to go back to this part of the sky and look for more. So this is excitement now, right? People are like, ooh, what is that? Let's find out more. And then we see things like today, right now, NASA convened the UAP, the Unidentified Aerial Phenomenon Panel, a couple of years ago, and it gave its report last year. Everyone's super excited about the idea of looking for life, right? That's exciting. But what would it mean if we found out that there was life? Okay, how would it change how governments fund things, right? You know, I tried to find a nice pie chart last night of the US budget, and it was so depressing that I didn't put it in. NASA's funding over the last decade, I don't know if you're aware, has not kept up with inflation. It has not kept up with, for instance, 2020 spending. Flat is the new down. And if we stay flat, that'll be great. But if we found life on other planets, would that change what governments spend their money on? Would it change? Would they spend more on defense? Would they spend more on science? Would they spend more on engineering, right, to send things out? How would it change what governments spend money on? How would it change religion? You know, these are religious questions that people have been thinking about for a long time. So Isaac Newton, you know, quite famous scientist, also quite ardent religious person. And he only a couple of hundred years after Giordano Bruno, saw no conflict with the idea of exoplanets and God. He was just like, God is infinite, there's lots of worlds, God made them all. Like, what are we arguing about? But clearly there were people arguing against that, why Giordano Bruno got burned at the stake. So how would it change religion? How would religions incorporate this into their theology? Right? What would be rewritten? What would change with religion? What would change about how we treat the Earth? Right? Earth is the only Earth-like planet we have. It's the only place we know we can live. Would it change how we treat the climate? Would it change how we explore space? Would it change how we keep our space clean? What would it change about how we think about the Earth if we knew there were other Earths out there? And I'll stop here and say a lot of people are like, will we ever get to them? Space is big and physics is mean. We are not going to get to an Earth-like planet. Even if we find it in 20 years, we are not going to get there. There's no way that doesn't break the laws of physics to get to these planets, except generation ships, which means our grandchildren's 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 grandchildren are getting there, right? That doesn't break the laws of physics. Might break engineering, but doesn't break the laws of physics. So how would it change how we treat our planet, knowing that there were other Earth-like planets out there? And then finally, individually, how would it change a single person to know this? So I will feel joy. I have been thinking about this and hoping for this for so long. And the idea that there is company out there is a marvel to me. It's a wonder. I will feel so much joy. That's not everybody is going to feel that way, right? Like some people might be scared or don't care. It's just like, I'm going back to my grocery list. Some people won't care. So I'll leave it by saying, how will you feel? Thank you very much.